It's my honor to present the second plenary speaker, Professor Nele De Belie from Ghent University in Belgium. She is professor in durability of cement materials since 2000 and director of Mme Nele De Belie Laboratory for Structural Engineering and Building Materials since 2020. She is Vice President of RILEM, outgoing chair of the Technical Activities Committee. She is the author of more than 300 publications and 20 book chapters, editor of 10 books, inventor in 3 patent applications, and editorial board member of 3 scientific journals. She is laureate of several awards, such as the Rabat medal. She will give her plenary lecture on understanding the carbonation of concrete with supplementary cementitious materials. Would you do the honor, Professor Nele? Thank you.
Okay, thank you very much for the kind introduction. Thank you for inviting me. Thank you to the organizers for inviting me for giving this presentation. My presentation will concentrate on the understanding of carbonation of concrete with supplementary cementitious materials, and it's actually work that came out of the RILEM Technical Committee of that name that I'm currently chairing. So I also want to acknowledge my co-authors who have made an important contribution, and of course also all the committee members. Actually, the talk of the previous presenter, Karen Scrivener, was a very good introduction to my presentation, because indeed I also wanted to start with the carbon dioxide emissions that are related to the Portland cement production. And indeed, as she has mentioned, a large amount of those are related to combustion, but an even larger amount due to decarbonation, so the decomposition of calcium carbonate into calcium oxides, which we need in the clinker, and carbon dioxide. So there have been a lot of discussions lately, for instance in San-Euro, to reduce indeed the carbon footprint and come to net zero emissions even by 2050, and clinker substitution is part of the solution indeed. You might recognize these slides, which I borrowed kindly from Karen Scrivener, because indeed we want to move to more substitution of clinker by supplementary cementitious materials. And the ones that are currently in use is indeed limestone, fly ashes, slag, silica fume, natural pozzolans, and more also those calcine clays, which you already heard about. Now, there is one thing, indeed, if we change the composition of the Portland cement and we start to introduce more supplementary cementitious materials, that we actually change the composition of the hydrates, and that, well, importantly, we change the amount of Portlandite in the composition. And here you see some of our previous work where different amounts of clinker have been exchanged by 30, 50 or 85% of blast furnace slag, and although at lower substitution levels the same amount of water is bound after a certain time, you do reduce the Portlandite content in the mix. At early ages this is not so pronounced, because actually the presence of slag is enhancing the cement hydration, but at later ages you do reduce drastically the amount of Portlandite in the hydrate assemblage. For slag, there is still limited consumption of this Portlandite because this is a latent hydraulic material. But if you move to the use of fly ash, for instance, then you can clearly see if you would use higher amounts of fly ash, going from 30%, which is more often used, to higher amounts like 50%, 65%, that over time, after a few years, actually the portlandite content goes down to even 0. And this, of course, has some effects on carbonation resistance because portlandite is an important buffer towards carbonation. And we can see that for mixes with supplementary cementitious materials, carbonation rates are increased, and this might lead to faster corrosion of reinforcement once the carbonation depth reaches the reinforcement. However, there are many different parameters influencing this process, for instance, the curing age, and it should be said that in accelerated tests to check for carbonation, we actually concentrate all the carbon dioxide attack on the concrete at early ages. And this is at the moment, especially for mixes with pozzolanic additions, when the microstructure has not fully developed. And you can clearly see here, for instance, if you look at carbonation rates, again for concrete types with just Portland cement and then with 50, 70 and 85% of slag, if they only have been cured for 1 month and then you really submit them to an accelerated carbonation, that the carbonation rate will increase drastically with the replacement percentage. However, when you cure them longer before you apply this accelerated carbonation, the carbonation rate can actually go down a lot, and this might be more realistically if you compare it to the real situation where carbonation is more gradually going on over the service life of the concrete. Now, first of all, in our Ryland Technical Committee, we have started, like Nicola introduced, state-of-the-art analysis is very important. We have started with an extensive literature review about carbonation in concrete with supplementary cementitious materials. So in our technical committee, we have over 100 members coming from more than 20 countries, and we have established different working groups, and at the moment I will only mention the work of working groups 1 and 2, but if you are interested you can find already published articles in Materials and Structures about, for instance, the combined effect of loading and carbonation, about corrosion-induced carbonation, and also carbonation of concrete with alkali-activated materials. So I will start with giving an overview of the state-of-the-art that we brought together in this state-of-the-art paper where we checked 209 references and worked on it with 21 authors. So this has been published in 2020 in Materials and Structures, and if time allows, I will then also give a bit of information on the round-robin test we started then after that review. So actually, important parameters to consider if you look at carbonation of concrete with SEMs are, for instance, the carbonation kinetics, effect of the mix design, effect of the curing conditions, effect of environmental conditions, and then how does carbonation actually itself influence porosity and transport properties. So to start with the mechanism of carbonation, actually, thermodynamic modeling is a very good tool to get some insight on what's really happening. And this is just the overview what is changing if carbon dioxide is bound in, well, in this case, a white Portland cement paste. So we have to go actually from the right to the left of this picture, and then you can see in this cement paste there is quite some Portlandite available. And if carbonation is starting, actually this Portlandite is transformed into calcite. And at the right-hand side, at the same time in this image, you can see what are the related drops in pH in the black curve and then in the more gray curve. What is the change in calcium-silicon ratio in the calcium silicate hydrates? So as long as Portlandite is reacting, actually the pH is more or less stable, and also the calcium-silicon ratio. But then if all Portlandite is transformed into calcium carbonate, other reactions are starting, and most importantly, the high calcium CSH is transformed into decalcified CSH. So calcium oxides are taken from the CSH to form more calcite. And that means that at this time, actually the pH will drop first slowly, then more rapidly, and at the same time, actually, the calcium-silicon ratio in the CSH will go down. Other reactions happen as well. For instance, the monocarbonate will be transformed into straplingite, which will later also become unstable. attringite will become unstable as well. And then finally, the decalcified CSH, when the pH is going down to a level of about 10, will further be transformed into silica gel and calcite, which will, of course, have also an effect on the properties of the material. So you will have a related very big drop in pH and a drop in calcium silicon ratio of the CSH. So actually, this is the thermodynamic model, but what is happening in reality is that not all the portlandite is carbonating before CSH carbonation is starting, because you have the precipitation of calcium carbonate, as you see here, on the portlandite surfaces, and this actually forms a layer which limits the further diffusion of carbon dioxide towards your portlandite, and also the further diffusion of water, which is needed for dissolution of carbon dioxide and for the whole carbonation reaction to happen. So, what about carbonation kinetics? Well, actually the processes happening here are quite similar for cements with supplementary cementitious materials, but you have, of course, initially a lower amount of portlandite available, so you will more quickly move towards CSH decarbonation as well. Now, carbonation kinetics, that's mostly based on Fick's first law, so you can model the carbonation depth as function of the square root of diffusion coefficient and carbon dioxide concentration at the surface. And then in the numerator, you have the amount of carbonatable material. So actually, you can transform this equation to just the carbonation coefficient multiplied by the square root of time. But this is hypothesizing that you have a fixed carbonation coefficient, which in reality may not be the case. Because actually, the microstructure may also change during the carbonation process. And then the carbonation rate itself becomes also a function of time. And then this exponent n here can be negative or positive depending on what's happening with the microstructure. For instance, what usually is happening is that if you carbonate portlandite into calcium carbonate, you form a product that is more voluminous than the original reagent, so you actually get pore blocking. And then the exponent will be smaller than 0. On the other hand, if you have, for instance, carbonation shrinkage and crack formation, then the exponent here will be larger than 0. And what we often see that in Portland cement systems, carbonation is indeed resulting in pore blockage, but if supplementary cementitious materials are present, it might lead to an increased porosity because you more rapidly start to carbonate the calcium silicate hydrates. Carbonation will also depend, of course, on the mix design, and we have already seen that in the ternary diagram, if you add different SEMs in the picture, they have a different oxide composition than the Portland clinker, and their reaction will also lead to other hydration products. So actually what's happening, if you add supplementary cementitious materials, you have on the one hand a filler effect and a dilution effect. So you have at first stages an increase of the clinker reaction because you have deposition of your reaction products on your clinker grains, and also dilution, you have more water, so you have more acceleration of the Portland cement hydration. And then when you add SEMs like fly ash, metakaolin, silica fume, blast furnace slag, they go into a latent hydraulic or pozzolanic reaction in the second step, and you get more CSH with a lower calcium silicon content, but also a refined pore structure. Additionally, you will get a reduced pH because you bind portlandite, and a reduced sodium and potassium contents in the pore solution, and we also often see an improvement of the interfacial transition zone between the water and the aggregates. Now, what is important for carbonation, which I want to add, if you have SEMs, it's not only that you move faster to carbonation of the SEH, but if there is aluminium present in the SEMs, you have rather a cache gel containing aluminium than a pure CSH, and apparently this might carbonate faster than a comparable CSH. On the other hand, there are some secondary reaction products like magnesium aluminium layer double hydroxides, which may improve carbonation resistance, and this effect is not yet fully understood. It's also mentioned in literature that with this cash carbonation, you might get increased carbonation shrinkage and also other polymorphs being formed of calcite, so not only of calcium carbonate, so not only calcite, but also more aragonite and vaterite. In this overview picture we just brought together some idea of how the clinker replacement level is affecting the carbonation rate in comparison with plain Portland cement for different clinker replacement levels. And then you see if you have SEMs, carbonation rates are increased, but it's for instance much faster for mixes with fly ash than for mixes with blast furnace slag. But on the other hand, of blast furnace slag we often use higher contents than in the case of fly ash. Now, how do we relate or how do we express or study the carbonation resistance of mixes? Some authors base it purely on strength or permeability, but then of course you overlook the carbon dioxide binding capacity of your mix. So other ways that it can be considered is to relate the carbonation rate, for instance, to the water binder factor and the clinker content. And then of course if you have too much water in your mix, you get increased porosity and increased carbonation rate. And then all these different curves, when they are higher up, it means that there is a lower clinker level, so you have also an increased carbonation rate because you have lower buffering capacity. Another way to consider this is that you just plot the water cement equivalent ratio, where you add your addition, actually your SEM, with a certain efficiency factor. And then this efficiency factor can be for slag, for instance, 0.6, 0.8, for fly ash around 0.3. And this then gives, but with quite some margins, a reasonable correlation. And then a third way to consider this is to plot the carbonation rate against water over the reactive calcium oxide in the mix, which also gives a reasonably good correlation. It's maybe the most scientific approach because you really look at all the calcium oxide that can react not only in the Portlandite but also in the CSH. So it's actually the total calcium oxide, but you have to subtract the calcium carbonate that is initially present, and then also calcium oxide and calcium sulfate and unreacted clinker and SEMs. But that does not take into account changes in porosity, of course. So it's also not a complete picture that you get in this way. If we consider mix design, something that we also checked in literature was the effect of aggregate volume and grading, because in the lab we often do accelerated tests on mortars and paste, because that's of course taking much less material and work than making concrete. But what is now the relation between carbonation of mortar and concrete? Can we just take our results of carbonation rates from mortar and transform these into rates for concrete? And then actually you find contrary results in literature. There is quite some literature stating that carbonation rates increase with the addition of aggregates and coarse aggregates, which is then explained by the presence of the porous interfacial transition zone around the aggregates, making the transport processes go faster. On the other hand, there are also some papers saying, like in this graph, that if you relate the carbonation coefficient of concrete to the one of a mortar or a paste, that it actually increases if you leave out the aggregates. Now, this could then maybe be explained by the fact that these mixes might be prone to a carbonation shrinkage, leading to cracks, and in this way to enhance transport properties. What about the use of other types of aggregates, like recycled aggregates and lightweight aggregates? Well, recycled aggregates are mostly found to give an increased porosity to the concrete. On the other hand, there is the factor of the adhering mortar in the recycled aggregates, which may not be fully carbonated, so the fact that you have some additional buffering material. But mostly the greater porosity is having the most important effect, and we see an increased carbonation rate if you add coarse recycled aggregates with a factor of up to 2, and even more if you have fine recycled aggregates in the mix. On the other hand, apparently lightweight aggregates, there the internal curing effect is dominating. So in a fresh mix, these lightweight aggregates are absorbing water from the concrete mixture and then later slowly releasing it to provide internal curing to avoid self-dissipation, so that you get a really good quality interfacial transition zone, and that actually the gas transport is reduced rather than increased. What about curing effects? So more curing will densify, of course, the microstructure. So that's the most important effect, that more curing will slow down the carbonation reactions. And actually, a sufficiently long curing may offset for the negative effect of SEMs on carbonation because of the reduced buffering. Like I mentioned, for tests in the lab, you really have to take into account that you do not concentrate all your carbonation at an age when the microstructure of the concrete with SEMs is not fully developed yet. What's also seen is the importance of the curing method. For instance, water-cured samples seem to have a much higher carbonation resistance than air-cured ones. And also the curing temperature, if it's increased like up to 60 degrees, it also increases the carbonation resistance. So this means that if you are living in a warmer climate, this might also have an important effect, and you may not just take the results of carbonation tests at 20 degrees. So here, just some images showing for different mixes of Portland cement with slag or with fly ash, the relative carbonation rate versus curing at 7 days. And then you see if you cure shorter, actually for all mix types, it may increase the carbonation rate with a factor of more than 2. On the other hand, if you cure longer, like up to 28 days, you may decrease by a factor of more than 2. So it is really a good investment for the future durability of a structure to cure a few days longer at the start, because it's really an investment in future resistance of your structure against carbonation degradation. What about relative humidity? So actually, the optimum relative humidity for carbonation is in a wide range between 40 and 80%, more specifically, mostly between 50 and 55%. But this may also depend on the type of supplementary cementitious materials, because here, for instance, at the right-hand side, for a sand 5 paste, you can see that depending on the temperature, the maximum carbonation rate may be at a different relative humidity value. Also, temperature has other effects, like it accelerates chemical reactions, also carbonation, but it also dries out your structure. And then, drying out, if the relative humidity is dropping below this critical value, the carbonation rate will decrease. Furthermore, the polymorphs that are formed may be different. At high pH, you always have calcite, but then at low temperature versus high temperature, you might have different proportions of the vaterite and the aragonite. Carbon dioxide concentrations is often increased in accelerated tests, but is this a good way to study carbonation? That's always the question. And actually in standards, previously also in our lab, we tested at 10% carbon dioxide, but it is often mentioned that you really change the mechanisms in that way, and that this is not a good way to accelerate carbonation, so you should remain below a certain level of carbon dioxide if you do not want to change the mechanism. Because indeed other things may happen at increased carbon dioxide concentration. For instance, more calcite precipitation on the surface of the portlandite. For instance, more rapid CSH carbonation versus portlandite carbonation. Different polymorphs that are formed. Furthermore, carbonation is a reaction in which water is produced. So this means water production. It may mean saturation of the concrete pores, and hence a slowdown of the ingress of carbon dioxide in the material. So this might counteract the faster carbonation that you might normally expect at high carbon dioxide levels. So it's not always easy as well to correlate accelerated tests to natural conditions, because in natural conditions, for instance, certainly if it's unsheltered, you have rain. And rain means again saturation of the surface layer, so a huge decrease in the carbon dioxide ingress. So they found in reality the relation between lab carbonation rates and the ones you find in unsheltered condition, an R square of 0.15 only is found, which is quite low. Okay, and actually, if you consider the presence of SEM, the literature is still undecided if accelerated carbonation is now worse for concrete with SEM than for Portland cement concrete. So opinions are divided there. Maybe something on the effect finally of carbonation on porosity and transport properties. So actually what I already mentioned is that carbonation produces calcium carbonate, which is taking a larger volume, so you get some pore clogging. On the other hand, the SEMs might lead, when there is carbonation, to some pore coarsening because you start carbonating the CSH. If you have aluminium and in the SEMs, this might also have an effect, and also carbonation shrinkage might be into the picture. Actually here it is seen that if you look at, for instance, the effect of water saturation in plain Portland cement and blended cement samples, that you have a different effect on the pore structure. Actually here, for the plain cement, these are absorption isotherms, not much is changing with carbonation, whereas if you have SEMs present, there is a difference between the carbonated and the non-carbonated samples, which means that actually there is an implication for the changes in pore structure, and you have more coarser pores also in the considered region here. What about transport properties? Well, here it is clear. The black bars are non-carbonated, grey bars fully carbonated. For Portland clinker, Portland cement with possibly addition of limestone, carbonation leads to a small reduction in the fusion coefficients, whereas if you have mixes with silica, fume or slag, it might be an increase. But since you start at a lower value, actually the final value may not be all that different. Similar for the sorptivity, non-carbonated and then partly carbonated, a decrease for mixes with Portland cement or low amounts of fly ash and blast furnace slag, but an increase if you have, for instance, 50% slag. So to conclude, actually for this literature review, the carbonation mechanisms in systems with supplementary cementitious materials are different than the ones of plain Portland cement systems. You have differences in phase assemblages, pore structure, pore solution chemistry, and very important here is the role of the Portlandite carbonation, because with these SEMs you will have less Portlandite available. What does this mean? Less buffer. It's also the main contributor for water release during carbonation. Carbonation of Portlandite leads to a reduction in porosity, but Portlandite carbonation may be in reality incomplete by discovering of the Portlandite crystals with calcium carbonate. With reduced content of Portlandite in SEM-containing systems, carbonation will go more rapidly, certainly if you have cash instead of pure CSH, which will lead to a coarsening of the pore structure, maybe some carbonation shrinkage, but actually there is still room for further research because some of these aspects are not fully understood yet. For instance, what is the role of the secondary phases that might have a positive effect against carbonation, like layered double hydroxides and so on. Regarding the correlation of carbonation rates of paste mortar concrete, also be careful when you just want to take the carbonation coefficients of your mortar as the ones of concrete, because it's not exactly the same. And also in reality, temperatures may be different, and this is an effect that is often overlooked. Well, actually, I think time is running out. I had a short overview also of our interlab comparison that we have made, but I think I will keep this for a future presentation. Maybe I will just scroll to the end. so that you can see also the reference of this publication. And maybe just for the ones who are interested in the difference between mortar and concrete, I want to add that this intellect test also sheds some light on this, because here in a test with samples that were analyzed by over 17 laboratories, we found actually indeed that the carbonation rate of mortar is smaller, about 80% of the one of concrete. So thanks for your attention.
Thank you very much. Really, it's a very interesting presentation. We understand really about combination. As you know, the most important thing is for the strength, it's the durability, and most important for us. And the bottom line to regard our infrastructure, mostly due to the corrosion coming from chloride and carbonation. And we can see very importance of carbonation. We separate the specific material and also about the standard, the test is very important. Curing, because it's very important. If you pay attention, then you can improve the problem of carbonation. I will say we are late and we will allow only one question. Please. Any question? Okay. Sit at the front. Very short question, please.
I'm coaching from National University of Singapore. I'm interested in one statement you made, that the carbonation of CaSH is faster than CSH. Is it just a phenomenon when you have gas polyandrite in SCM blended concrete cement paste, or it's a direct measurement of CaSH itself?
It seems to be related to the aluminium content in the gel. But this is what we found based on literature review, so it would be best to refer to the original publication to see if they really did the study on pure gels or in the mix itself, in the complete mix. But I can refer you to the reference if you like.
Okay, thank you very much. I think we need to move on.